Hello, and welcome to today's Research for Industry lecture series. I'm Peter Olsen. I'm a principal research scientist in RFI, and I will be your host today. Please remember to post any questions that you have during the talk, and you can also vote on the most interesting questions. We'll then address the most popular questions at the end of the talk. Today we have one of the world's authorities on hydrological modeling with us today, Dr. Stephen Frey. Dr. Frey is the Director of Research Services at Aquanty and an adjunct professor in the Earth and Environmental Sciences at the University of Waterloo. His research at Aquanty focuses on the application of advanced structurally complex HydroGeoSphere models to address today's and tomorrow's societal water resource challenges. Dr. Frey actually visited us on Redmond campus pre-pandemic in 2019 and gave a very exciting talk. He's now back with significant advances and a talk titled Physics-based groundwater surface modeling at continental scale. Please join me in welcoming today's speaker, Dr. Stephen Frey.
Thanks, Peter. So I guess we'll begin the presentation. And as Peter mentioned, today's topic is physics-based groundwater surface water modeling introduction at the continental scale. So this is work that we're doing at Aquanty, and it's really an evolution over many people's research and a long time. So let's see. So I'd first like to acknowledge the entire Aquanty team. I have the privilege of being the talking head here today for a lot of smart people that I get to work with. Also, I'd like to acknowledge the supporters and collaborators we have at Natural Resources Canada, the Geological Survey of Canada, Agriculture Canada, our provincial governments, many graduate students that have worked with us over the years, as well as others. And also, I'd like to extend a thank you to the Microsoft research team for inviting Aquanty to give a presentation here. So before we get into the nitty-gritty of modeling, I'd like to just give an overview of the hydrologic cycle. So I've clipped this picture from the USGS, and really it highlights what's going on with our hydrologic environment. So there's the above ground hydrology, which we're all really aware of. So that's the rivers, the soil moisture, rain and snow, melting and falling from the sky to kind of drive the surface water system that we see. But below the surface water system sits groundwater, and groundwater is a very important store of potable water for urban and rural water supplies. It supplies irrigation. It supplies surface water in times of drought, and it's often overlooked. And what we're talking about today in fully integrated modeling is a complete analysis of the holistic hydrologic cycle, including that of groundwater. So we've got everything that you see above the ground in your day-to-day lives, but we're also talking about what's going on below ground. And as we move forward under changing climates, what's existing in our groundwater stores below ground is going to become more and more important. So a little bit of background now on hydrologic modeling. So there's been an evolution of hydrologic modeling tools, I would say over about the last 40 years. And it began really with very simplistic lump type surface water hydrology models, non-PDE based, but more just a routing type approach where using some empirical relationships and some rainfall estimations, you would estimate how much water moves over the different areas in your model into the streams and channels, and then moves down gradient with some sort of a channel flow equation. And then that evolved into a PDE-based overland flow solution. So these become more numerically complex, but still they're only dealing with the land surface and what's going on in the land surface. They're not taking into account what's happening below surface. Now, another field of modeling evolved where it was looking at groundwater, and these began as fully saturated groundwater models that would take into account aquifers and aquatards being the layers of the subsurface that restrict water movement, and aquifers being the areas of the subsurface that provide potable water. Then the fully saturated models evolved into variably saturated models, so we could take into account how the unsaturated zones, so the soils and the shallow subsurface where there may be a mixture of water and air within the pore space of the porous media exist. So those tools evolved, and that kind of happened independently of what was going on with the surface water models. And then along came the coupled groundwater surface water modeling, which is kind of the latest advancement in the hydrologic modeling community. And this is where we're coupling groundwater with surface water in a single simulation. And there's loosely coupled models, and I've listed a couple here. And when I say loosely coupled, this is really a surface water model coupled to a groundwater model with some explicit linkage. And from there, it's evolved into tightly coupled models where we're solving the surface water equations and the groundwater equations implicitly, and the full dynamic behavior and interchange of groundwater and surface water can occur in response to some very subtle hydrologic forcing. So this is really where we are now in terms of the state of the science. It's with tightly coupled, fully integrated groundwater surface water models. And that's what Aquanty and the team does very well. So I talk a bit about groundwater already, and why do we want to talk about groundwater when we're thinking about the hydrologic cycle? Well, it's very important, and it sustains food production over large parts of the globe. And it's no secret that when droughts strike in some of these key food producing areas, the global food supply is at risk. And there's lots of headlines to support this this type of understanding. And China is heavily dependent on groundwater for irrigation. The US is heavily dependent. India, very dependent on irrigation from groundwater, as is parts of Canada. So we really do want to take into account the groundwater system when we're looking at long-term sustainability of our water resources, because that's a key linkage to food production. So now a little bit of background on Aquanty. So we were founded in 2012 by Dr. Ed Siddiqui here, my boss, who was a longtime professor at the University of Waterloo. And then when he retired from the University of Waterloo, he founded Aquanty and started building this staff of experts. And now we're at 22 expert staff that span a wide variety of different disciplines within the Earth system sciences. So we have climate modelers, we have mathematicians, computer scientists, hydrogeologists, hydrologists, soil physicists, contaminant hydrologists, and geospatial experts. And what we have now is a core team with expertise that spans the full extent of the hydroclimatological system. So we can really put experts in at any position on some very complex problems to work collaboratively to figure out some rather tough solutions. So it's an excellent team, and really world renowned, and a lot of the staff publishing in key journals along with doing their research at Aquanty. So Aquanty was founded on the HydroGeoSphere model. So it's the best in class fully integrated groundwater surface water modeling platform. It simulates the entire terrestrial hydrologic cycle. So really, once one of these models is built, the core driver is the weather or climate information that you want to provide. The model itself closes the water balance, and it takes into account whatever falls on the land surface, either moving over the land surface, infiltrating, and moving through the groundwater out into rivers, or transpiring through the vegetation cover, or evaporating off the land surface back into the atmosphere. So this is the full hydrologic cycle that's captured in HydroGeoSphere. This model is really governed by physics, and that gives it some unique capabilities to be used for scenario analysis, where some more empirical type models would tend to be weak with that type of application. We utilize irregular and unstructured 3D finite element meshes that allows us to put spatial resolution into the models where it's required, and reduce the resolution where it's not, to make for more efficient numerical solution. And it's a fully parallelized solution that leverages cloud computing and HPC. So a little bit of history on integrated modeling here. So the concept of using computers for simulating the hydrologic cycle began in 1964 and was evolved by Al Fries and Dick Harlan in really a seminal paper in 1969, where they kind of conceptualized using computers to simulate the fully integrated groundwater surface water system. And from this work, Al Fries went on from his career in Canada to go work for IBM at the Watson Research Center, where he had access to some of the best computing at the time. And they started running fully integrated models, and their model domain was a simple cross-section through a stream, hill slope terrain. And they were looking at the interactions between the stream and the stream bank and the groundwater system in the vicinity of this stream. A very, very simple problem by today's standards was what they set out to do in 1971. And they were running on these large IBM computers, and they were limited to about 30,000 nodes in these problems. So 30,000 nodes in their finite element meshes was about all they could handle. And just keep that number in mind later in this talk when we start talking about the model domains that we're dealing with now. So this is, of course, evolved over the last 40 years. And in 2010, a group out of Germany started really testing the opportunities to use the best supercomputers for running large-scale hydrologic problems. So they were running on a Blue Gene Q system, and they were running problems that had on the order of 1 billion finite element nodes. So really, the advancement in computational capabilities has propelled groundwater surface water modeling farther and farther forward. And now there's a number of these types of models available globally in the scientific research. There's comparisons on how these different models behave under some benchmark problems, and it's really kind of a maturing field. So when we look at a cross-section through a fully integrated groundwater surface water simulation, what are we seeing? Well, we'll use this animation as a small guide. And as it resets here, what we're going to see is some precipitation falling in an upland area. And then that precipitation initiates a hydrologic response at the land surface. We'll have some down gradient flow. So water always wants to flow from high potential to low potential. And that includes moving through the subsurface. So here we have the surface wetting up. We have an infiltration front moving water down through the subsurface into the underlying aquifer. And then we also have the down gradient flow filling up the depressions and ultimately moving off into a river. So that's essentially what we're capturing in a fully integrated groundwater surface water model. And in terms of comfortable model sizes, well, I showed you that example from Germany where they were working on the billion node problems. Comfortably now, we're running these models with anywhere from 2 to 5 million nodes on high-powered workstations. So typical cloud computing resources where we have Xeon chips, those are fine resources for running these types of problems, and we're making more and more use out of cloud computing to run these types of simulations. The types of equations, this is just a little snapshot of what we're solving in terms of the numerics. So we've got a PDE that looks after groundwater flow. So this is essentially a conservation type equation that takes into account the properties of the porous media and the hydraulic gradients to drive fluid from high pressure to low pressure. Then we've got a diffusion wave equation that governs the movement of water over the land surface. And then there's a flux component to that takes into account the the depth of water and the roughness of the surface. And these two equations, these two PDEs, are then coupled in an implicit numerical solution. So this is just a very quick snapshot of the type of mathematics that sits behind a HydroGeoSphere model. Now I'm going to walk us through how these models are built. And this used to be a very complex task to build these types of models. Processing the data, conditioning it, doing the QA, QC was a lot of effort. But as big data becomes more and more amenable to different scientific communities, it's becoming easier and easier to get your hands on the data to build these types of models, and then really it becomes almost like a recipe book that's followed. So in this case, we're going to look at a small 2,000 square kilometer watershed in central Canada, just north of the USA-Canada border, and look at how these models are constructed. So at the heart of a model is the finite element mesh. So these little triangular elements that we see here, the really triangular prisms that they project into 3D across a number of different layers. In this case, it's 10 layers. This is basically the framework for the model, the wireframe mesh for the model. And then we have to put the different components in. And the wireframe is constructed in such a way that we put detail where we need it. So here we have 50-meter resolution along our surface channels, and then up to 150-meter resolution out in the open agricultural spaces. Once we have our wireframe mesh designed, then we have to configure the stream network. So we have these stream channels. They're hydraulic features in the model that route the water through the system, and they interchange water between the overland flow domain and the subsurface. They have to be parameterized. So we pull in this vector data to define where our river channels are. We pull in land cover data that describes, say, the leaf area index for the vegetation. It describes the types of land cover we're dealing with in our area. So here we have forests, wetlands, lakes, a lot of agricultural land. We have some wetlands. All of these different types of land surfaces govern water movement in a different way. That has to be taken into account. The soils are also a key component of any integrated model. Different soils have different ability to transmit water. They have different abilities to hold water as they dry. And that becomes really important when we look at the plant uptake of water, as well as the infiltration of water through the soil profile into the deeper groundwater system. So when we build these types of models, we take into account the spatial distribution of the different soils and their associated hydraulic properties. So there's some features on the land surface that are too small to be resolved in our finite element meshes. So when we're dealing with watersheds in the order of thousands, tens of thousands, or even hundreds of thousands of square kilometers, sometimes some small scale features can't get resolved with the physics. And that's where we use subgrid process representation. And in this case, what I'm showing is the ability to capture wetland features in small potholes. So these are features that are on the order of maybe 50 meters in size. They have an impact on the hydrologic behavior, but we can't resolve them physically. So we use this subgrid process representation with real storage. So we have an equivalent water holding capacity for each one of these triangular elements in the overland flow domain to hold water. And that's just one example of how we're working to incorporate small scale features into large scale models. And this gets really important when we start moving to the continental scale, which we'll talk about in a few minutes here. And below the soil layer comes the hydrostratigraphy. So hydrostratigraphy is this sequence and distribution of geologic materials that have different hydrologic properties. So you can have aquifers that permit the easy movement of water and provide a water source. And then we have aquitards that restrict the movement of water. And this is really what we're looking at now, the assembly of the different aquifers and aquitards in the subsurface component of this model. And when you take the subsurface component, combine it with the surface component, then you've got the fully integrated groundwater surface water model. So once it's built, you of course have to test it to make sure it's fit for the purpose you have in mind. And that's where observation data becomes increasingly important. So in this case, we've got groundwater wells located across the watershed. These are the green dots. We've got a watershed outflow location, and then we've also got some surface water monitoring locations. And what we do then, we run the model for a certain interval of historic time, and then compare how the model behaves relative to our observation data. And we want to go through this step to make sure the model is indeed suitable for the purpose we have in mind. And we use statistical metrics and time series analysis to make sure that the model is doing what it's supposed to do before we put it to use in whatever application we have in mind. And here we're showing the ability of the model to track the surface water flow variability over flood years, drought years, and more flood years, and also to capture the groundwater elevations in the individual groundwater monitoring wells. So now that we've validated the model, we want to put it to use. And I'm just showing an example here of how a scenario analysis might be applied towards one of these models. So we took the model that we had built for that subject watershed that we just looked at, and we changed the land surface configuration. So we took some wetlands out of the model, we added more wetlands back into the model, we changed the soil health. So we changed the permeability and the water holding capacity of the soil, and then we run different types of scenarios. So we run flood scenarios and we run drought scenarios, and we look at how that landscape responds to those perturbations on the land surface. And we're looking at some outputs here for how surface water storage changes over time, given different land surface configuration, and how groundwater storage changes over time, given the different land surface configurations. And this is one of many examples of how these models can be used for scenario analysis to answer scientific questions. And up until recently, the fully integrated groundwater surface water models had really been scientific tools. And at Aquanty and our colleagues all over the world who are doing this type of work, we're actively publishing in the scientific literature to provide new insights on how the hydrologic system works. And this is at really the heart of Aquanty, and what we were all doing in academia before we joined Aquanty is we were doing the science. But now the science has evolved to the point where these tools can be used for societal endpoints. And this is where it really gets interesting, because now we can take everything we've learned from the science and apply it towards the application of fully integrated groundwater surface water models for day-to-day decision making. And now we're going to expand in spatial coverage, because when we're talking about a small watershed in a localized region, well, that's maybe useful for the people that live in that area, but it's not of broad interest to society. So basically the proof of concept to push this to a larger scale that is more relevant to society is Southern Ontario. So this is an 80,000 square kilometer area in southern Canada. It's got a population of about 12.7 million people. Groundwater resources are an important part of the hydrologic cycle. Here where I live, over half of the community relies on groundwater for the water coming out of the taps. Industry relies on groundwater, and groundwater also sustains a lot of the superficial hydrologic system during times of drought. So we've got this project. It was kind of a proof of concept to show a collaboration exercise between Aquanty and some government agencies who were really instrumental in furnishing the data to help us configure the subsurface components of these models. So now we have this proof of concept area in Southern Ontario that we're going to look at. And much like that previous model assembly process that we just walked through, we need key data sets. And these data sets are becoming more and more available at larger and larger scales. So again, it's not a stretch to build big models because the data is available. So digital elevation models, land cover, surface water networks, soil distribution, the subsurface hydrostratigraphy is all available to us here in Southern Ontario. And I have to give a big shout out to the federal government in this case and the Geological Survey of Canada, because they did a tremendous job in working to characterize the subsurface in our region so we could build this tool, and they've worked great collaboratively with us even now to this day. So we build the model, we pull in the monitoring data feeds, and I'll mention here we've got groundwater monitoring, we've got surface water monitoring, and a lot of this comes in real time. So now not only is it a historic data set that we can get our hands on to compare the model results to the real world, but we can also pull real-time data. And that allows us to test how these models are behaving on the fly as they run. And beyond the groundwater and surface water data, we're making more and more use out of remote sensing data. For these large models, in regions where maybe we don't have a lot of terrestrial monitoring, in northern expanses, in parts of Africa, parts of South America, there isn't a lot of real on-the-ground data available, but remote sensing is basically covering the planet. So we're using soil moisture data from the SMAP satellite, from the SMOS sensor, from the European Space Agency. We're using that type of soil moisture data to validate our models and actually cross-validate against some of the other products that we're using. And here I'm just showing basically a cross correlation between the satellite soil moisture from the SMAP, the passive sensor on the SMAP satellite, and HydroGeosphere's prediction for soil moisture storage at different depths within the soil profile. So we get very good correlation at a large scale between these remote sensing data products and HydroGeosphere. Another example is using the GRACE satellite data. So the Gravity Recovery and Climate Experiment is looking at changes in the Earth's gravity signal. We look at those changes in the gravity signal and relate it to changes in the water storage on the land surface and in the subsurface. And our collaborators at the Canadian Geodetic Survey, part of Natural Resources Canada, they're collaborating with us to do the correlation analysis. And again, we get very close relations between what we see from the GRACE satellite and what we see in terms of water storage in the HydroGeosphere model. So again, this is another mechanism to cross-validate some relatively large-scale remote sensing data to a highly resolved integrated groundwater surface water model. So I'll talk a little bit now about regional versus watershed scale and these types of applications that are really geared towards societal endpoints. So at the regional scale, which is basically that 100,000 square kilometer scale we just looked at in Southern Ontario, we can do a groundwater resource characterization. We can look at climate change impact analyses and how climate change is going to impact the large-scale behavior of the surface water and groundwater resources and the interaction between surface water and groundwater, and we can build an understanding of the regional groundwater flow system. But oftentimes what society is interested in are things like localized flood risk, persistence of drought conditions on their localized aquifers, drinking water quality, beach closures, these types of endpoints. And that's not necessarily something that can be teased out of a large scale model. It needs to be a smaller scale model. So for the day-to-day interests, we still have operational constraints when it comes to those big regional models. But what's really important is that once those regional models are built, those databases become available then for the assembly of smaller scale localized models in a very efficient fashion. And that's what this slide really highlights, is once you've got a regional model database assembled, you can go in and carve out sub areas from within that database and build small scale models. And those small scale models can carry higher levels of spatial resolution that allow us to resolve more detailed hydrologic processes, things like localized groundwater effects from ongoing droughts and water quality endpoints. That is available from a smaller scale watershed simulation. So this is really a database that facilitated a much more detailed hydrologic tool, which is what we're going to get to next. So once you've got the databases assembled and the automation tools to quickly build these localized watershed scale models, we can start thinking about how do we make use of all this modeling technology and data availability, the remote sensing data we have at our hands, the sensor data that we can get our hands on in real time, water management information, HPC, cloud computing, cloud-based dissemination of information. And what we've turned it into is a real-time hydrologic forecasting system for both groundwater and surface water resources. So in this case, what we're doing now is taking our HydroGeoSphere models, coupling them with weather forecasts and real-time data feeds to produce a forward-looking hydrologic forecast. Then we're producing these forecasts on temporal intervals anywhere from 3 days out to 32 days. So we're running sub-seasonal hydrologic forecasts now that provide insight for groundwater, surface water, and soil moisture conditions. And I'll mention too, it's not a purely deterministic forecast. We're actually running an ensemble of weather forecasts in the modeling so that we can produce an ensemble of hydrologic forecast outputs, which allows us to bracket some of the uncertainty with some statistical metrics. And that has become the HGS real-time, or HGS-RT, HydroGeoSphere real-time forecasting system. And we have the proof of concept running now for Southern Ontario, where I mentioned, producing the forward-looking operational forecasts for a number of different hydrologic endpoints. And this is all sitting on Azure. And just a quick snapshot, I didn't want to run this live because of the fear that the web may crash or the app may crash while we're going through it here during the presentation. So I've just got some static snapshots of what the tool looks like. So the users of the forecasting tool can click on their watershed of interest. In this case, it's an 8,500 square kilometer area just northeast of Toronto. And in different areas within the watershed, you can click on points and get information related to anticipated surface water flow conditions, anticipated groundwater levels, anticipated soil moisture conditions, and information regarding groundwater and surface water interactions, groundwater recharge and groundwater discharge. And I'll just point out again with groundwater discharge that during dry times, groundwater is an important mechanism to supply base flow into the rivers and streams, and that has a lot of value beyond just volume of water flowing through the river. There's ecosystem goods and services, wildlife, pollinators, habitat that are all dependent on water in these surface water features during periods where there isn't necessarily a lot of rain falling. So this is where knowing a little bit about future groundwater discharge conditions can help us gauge what the surface water system is going to look like and its potential to support ecosystem goods and services, waste assimilation from water treatment plants, that type of thing. So now we've looked at the proof of concept for Southern Ontario, so that's the HGS-RT platform. Now we really want to start thinking about how we employ this at the national scale. So this is even getting more and more interesting, more and more exciting now. So we've demonstrated the utility of these tools at a regional scale in an area where there's a large population. So we have the societal endpoints being met in Southern Ontario, but now we're looking at the entire country. And this is where a new and rather large collaboration and partnership between Aquanty, Natural Resources Canada, including the Geological Survey of Canada, the Canadian Forest Service, Surveyor General Branch, Canadian Centre for Mapping and Earth Observation, Agriculture Canada, and the University of Toronto and University of Waterloo have come together to basically expand what we've done in Southern Ontario to build a foundation for rolling that type of technology out across the entire country. And that's called Canada One Water. And it's a 3-year initiative that's just gotten started. And we're going to be working over the next 3 years to build these databases and models and run some climate scenarios. And there's a website associated with this project for anyone who's interested in more information. So objectives for the first 3 years are to build a full set of fully integrated groundwater surface water models for all of Canada. We want to use the models to evaluate the potential influence of climate change and the water resources at large scale. And then we want to work at translating the model outputs into some societal relevant metrics. And what we've done here is taken what is effectively a 10 million square kilometer model domain and divided it up into 6 major drainage basins. And within each one of these basins, the physiographic characteristics are similar. We have the St. Lawrence, we have the Hudson's Bay lowland, we have the Arctic region, Mackenzie, the Prairie, Northern Great Plains region, and then the West Coast. So we're going to build essentially 6 models that form the underpinnings for this modeling platform, each about 2 million square kilometers in size. And behind this initiative is a lot of dataset development, and that's where it's key to be working with experts at the government, because they're really the people who know this data the best. We can help condition the data for use in our applications and use by the modeling community, but it really is the government researchers who need to be involved in these types of processes, and we're very lucky to have a great team to work with. So we're assembling large-scale DEMs, drainage network, vector data, soil distributions, soil hydraulic properties, the hydrostratigraphic models, the hydraulic parameters, and the distribution of those parameters within the hydrostratigraphy. We're assembling all the validation data for the model. We're pulling in climatology. We're running additional climate models, as well as using model data from the CMIP6 and Cordex archives, and we're pulling in remote sensing data from a number of different sources. And we're harmonizing all of this data across the continental scale, so it'll facilitate easier model construction in the future. So beyond just HydroGeoSphere modeling, this Canada One Water initiative has 2 other modeling components. One is land surface modeling, where we're running the community land model to help estimate the thermodynamic exchanges between the land surface and the atmosphere. That becomes inputs to HydroGeoSphere. So we're not actually running thermodynamics in HydroGeoSphere at this scale. We're relying on inputs from the community land model to help us understand where the land surface is frozen, where it's thawed, where permafrost exists, and the dynamic evolution of the near surface landscape over annual cycles, and then under climate scenarios where the land is warming and the freeze-thaw profiles are changing. The inputs from the community land model also help drive regional climate modeling that we're doing in collaboration with the University of Toronto. And in that particular modeling, we're running the WRF Weather Research and Forecasting tool to produce future climate realizations using the best available science for our continental Canada domain. And then the outputs from the WRF regional climate modeling become the climatological scenarios for the HydroGeoSphere model. So when we're running climate change analysis with HydroGeoSphere, we take the thermodynamic insights gained from CLM, we take the climatology from the WRF model, and then we start driving the HGS models. And then the HGS model is what tells us how the surface water system, the groundwater system, and the dynamic exchange between groundwater, surface water will evolve under those different climate scenarios that we're interested in. So outcomes from the Canada One Water project. Again, this is just the first 3 years of the program. We expect it to go on much longer in time, but over the first 3 years, we hope to achieve state-of-the-art hydroclimatological analysis of climate change impacts across continental Canada. We want to provide decision support information to help guide agriculture, forestry, industry, and the rural community with their water resources planning. Right now, there really isn't a lot of that type of information available, so there's a need for it. We're providing a set of open source models and data to support future research initiatives. And that's one thing I would point out with the Southern Ontario proof of concept modeling that we did in collaboration with the Geological Survey of Canada and others. That model, along with all the data sets, was published as open source material, and now there's a generation of new researchers who are coming along using those models and the data sets to help facilitate their own research. And if you're a PhD student who has access to pre-assembled data and pre-built models, even if they're just a template for what you might want to create yourself, it really helps speed up the time between when you start and when you can actually start doing science. And then finally, and maybe most importantly for future ambitions, what we're creating here in Canada One Water is a modeling and data framework to support the deployment of HydroGeoSphere real-time across all of continental Canada. So with this data set built and the preliminary models assembled, we can quite efficiently start going in now and building forecast models for local areas across the country, or potentially the entire country. So with that, I'll take us to a summary of our talk. First of all, I'd like to state that fully integrated groundwater surface water modeling, it's evolved from primarily being a scientific tool to now being a real-world, real-time decision support tool. The availability of the requisite data required to construct these models and the validation data required to construct and validate, calibrate the models, it's no longer the constraint that it used to be. So there's in the modern parts of the planet, this data all exists. So the US, Canada, Western Europe, even parts of Africa, parts of Asia, this data all exists. And it's not nearly the challenge that it used to be to deploy these types of large-scale tools in what used to be relatively unmonitored areas. And even in regions of the world where monitoring data is sparse, there are still global data sets that help for model construction activities. So Africa, for instance, there's global DEMs, there's global river network data, there's global soils databases, there's even global hydrostratigraphy information. It may not be of the highest resolution, but it's good enough to help deploy these tools at a preliminary stage to become decision support mechanisms in areas that otherwise have very little guidance on future flood or droughts. Okay, and on from that, I mentioned also cloud computing and hosting. This is really key to being able to disseminate the outputs from what are really complex scientific tools and extremely complex hydroclimatological analysis out into the stakeholders. So the vast majority of the people who can benefit from the type of information that we're producing, they're not in a position nor interested in the actual underlying model, but they're really interested in the types of insights that can be gained from the modeling that we do to help guide their day-to-day activities and their longer-term planning. So with the cloud tools, delivering the information, and with our ability to build nice user-friendly apps, we can get this pretty hardcore scientific data out into the user community for broader consumption. So these types of tools then, they have the potential to play a key role in climate change adaptation, our ability to adapt to and plan for extreme weather events, so we can have some forward-looking insight on drought, prevalency, flood extremes. This can all be forecasted now, and then you can plan in advance. And my last point on this, and really the last point of the presentation, is that while the science has evolved into the point where we can deliver these types of data products to the broader society and we can provide the decision support information, it's really now a market development exercise as well, because most people don't know that these types of tools exist to produce these types of data sets that can be used for day-to-day activities to help plan around hydrological extremes. So with that, I will say thank you, and I guess open it up to questions.
Thank you so much, Stephen. This was a great talk, and now a lot more people are aware of these types of tools, and there's a lot of modeling inside Microsoft that I'm sure can benefit greatly from this. So while we wait for questions, let me just ask a preliminary question, which is that in oil and gas reservoir modeling, they also solve the Darcy and porous media equation. And there's a lot of excitement currently about using neural networks, in particular functional neural operators, to complement the physical modeling, especially because these methods can vastly accelerate modeling, but it's not as accurate. Is this something that you are looking into at Aquanty too, or is that not as useful for hydrological?
Well, that's an excellent question, and really, that's the next frontier in Aquanty's research and development ambitions. So we actually have machine learning experts on staff working with the universities to develop coupled modeling where HydroGeoSphere actually works concurrently with machine learning models to predict outputs that aren't being directly simulated in HydroGeoSphere, but have relationships to the hydrologic cycle. Water quality being a perfect example. So this year at the AGU conference, we're presenting a coupling between some machine learning modeling and HydroGeoSphere for watershed scale prediction of E. coli, so fecal indicator bacteria in surface water systems, as well as nutrient loading in surface water systems. So we're taking the outputs from HydroGeoSphere, combining it with machine learning, and then using the machine learning models to produce the predicted water quality endpoints. So yeah, we're definitely looking at how the physics-based modeling can be combined with the other data-driven type modeling approaches.
Yeah, very nice. And I guess right next door you have University of Toronto, which has really been one of the pioneers of this sort of modeling. Another question here is, do you also use subsurface seismic analysis of fractures for modeling?
So the modeling that I showcased here today, we're not discretely resolving the fractures in the porous media. It's represented with kind of a excuse me, an equivalent porous media type of approach.
Yeah.
But there are people who use HydroGeoSphere, and there's some of the leading work, I think, with fracture focused groundwater flow is using HydroGeoSphere, and you can use HydroGeoSphere with discretely resolved fractures to look at fracture influences on the groundwater flow system and on contaminant transport in the subsurface.
Right.
So while we haven't showcased it here today, HydroGeoSphere has the capability to take into account discrete fractures.
Yeah, very nice. So recently I was actually amazed to learn that they use airborne and spaceborne LiDAR to monitor the snowpack in Colorado that subsequently is used for forecasting and water management in the Colorado watershed, and that has enabled farmers to much better plan what crops and when to plant, and of course government management has been improved a lot. So can you talk a little bit about what you do for forecasting snow and how that impacts the watershed model?
Yeah, so we're pulling our snow data from a remote sensing. I guess it's kind of it's an assimilation product called SNODAS. So it's based on remote sensing, and it's giving us a snow cover estimate on a daily basis within the areas that we're running our forecasting system. So we're using that remote sensing based data to inform what the snowpack conditions are in our models. So then based on the upcoming air temperature conditions, we can anticipate with snow modeling how much of that snowpack is going to melt. So we'll melt the snowpack in our models to become an additional input to the hydrologic forecast. So in a case where you've got a snowpack and you've also got forecasted precipitation, so rainfall on the horizon, we'll be melting the snowpack and adding that water to the rainfall to become the hydrologic driver for the HydroGeoSphere forecast.
Yeah, thank you. I mean, this is such a complex system. It seems like it's almost getting out of control.
But you know, on that, you know, the beauty, and this is the beauty of the age we live, where we have all of this information at our fingertips. So the ability to pull real-time or near real-time snowpack data from a product like Snowdas and use it operationally, like it's awesome. And that's a product that's been, you know, quite heavily validated in different parts of North America. We've done some testing and some publishing on it as well, and you know, we have a lot of data available, and you know, really these modeling tools, they're like amalgamators of knowledge, and they can take into account physics that, you know, my brain just can't handle, but it really becomes, you know, fascinating how you can use all of the information at our fingertips to get a bigger picture understanding of the hydrologic system and how it's going to behave.
Yeah, your talk definitely highlighted the complexity and, you know, how much data is coming in. So and another question is, recently I learned that there's actually 3 scales that people are forecasting on. There's a long-term climate level forecasting, the short-term, you know, 1 to 2 week range, but there are also people doing midterm forecasting, which is you know, a month to 6 months ahead. And you talked about how you use the weather forecast a little bit, but how do you see these other ranges of scales, so to speak, affecting the future? I mean, I'm thinking in particular from the perspective of, you know, somebody that's doing farming in like a drought region like the west of the US. It's very important to have these longer term forecasts.
Yeah, so I can comment on that. And I've shown here, like we're producing a 7-day operational forecast, and that's produced daily on our system. And we're pulling the NCEP weather forecast to drive the HydroGeoSphere models. Then we're producing a 32-day forecast, which I guess is a sub-seasonal forecast. We produce that once a week. They're both ensemble-based forecasts, and we're doing skill analysis now. And this is we've only been kind of in beta testing mode for that sub-seasonal forecast for about the last 4 to 5 months. But we're doing skill analysis, and what we're seeing is that the groundwater system over the longer forecast interval has a longer term skill than the surface water system. So these forecasts are really only as accurate as the weather forecast. And the weather forecasts, they can, you know, be sometimes good, sometimes not so good, depending on the complexity of the weather systems, convective precipitation systems versus the frontal systems. You know, that creates some differences in the weather forecast skill. So we have to remember that the hydrologic forecast is really at the mercy of the weather forecast, but we do see, like over like 10 plus days, 15, 20 days in some cases, that the correlation between the groundwater behavior and in the forecast versus the observed groundwater behavior is quite good. So we're looking at linear correlations of 0.5 or above, whereas in some cases, you know, with the surface water system, 5-6 days out, we start to lose the forecast skills. So like I think as the weather forecasting gets better, the hydrologic forecasting is going to get better too. Right now, it seems we have better insight on long-term groundwater behavior than we do on longer-term surface water behavior, but this is very preliminary.
Right. Yeah. So we have a question from Pratmesh Prabhu here. Regarding market development, are there particular types of questions where you see modern modeling providing insights far beyond otherwise possible? In other words, could you talk more about the most marketable benefits from modeling that has recently become possible?
Well, I think flood and drought anticipation is a big one. We saw that in the western part of the continent this summer, where the drought really went on, and I guess in some areas is still going on. So using these types of tools to anticipate the drought severity, whether it's going to get better, whether it's going to get worse, how long it's going to take before you start to see a shift in things getting better or worse. This creates for better planning. So you're not going to correct a drought based on having a forecast at hand, but you can plan for the drought, or you can plan for the flood. You can move assets, you can move livestock in the case of the agricultural community. So planning, I think, is a big one. So anyone who needs to plan in advance of extreme weather, be it either too dry or too wet, I think they can make use of these types of products. Urban settings that rely on upstream water management to support things like base flow through the rivers in their communities, they can use these types of tools, because oftentimes they're managing water infrastructure. So they're managing dams and reservoirs to maintain a balance between recreational and more utilitarian uses of the water. So water management can benefit from having good forecasts. Ecosystem goods and services, like this is an emerging topic where, you know, putting an economic value to natural capital is becoming, like, really, it's almost an investment vehicle now, and I think in the future it will be even more so, like green bonds, those types of mechanisms for investments. Like, they need quantitative insight on how the landscape is behaving. So if you want to put an economic value on what a forest does or what a healthy soil does in terms of water conservation and ecosystem maintenance, then you need quantitative tools like this. And we can forecast that type of behavior in real time. So there's some example. Insurance is a big one. I think anyone who's insuring against large-scale climate risks in the short term as well as over the longer term, these types of vigorous quantitative tools, I provide them good actionable insights that otherwise they wouldn't have. So maybe that's a few examples, but I will say at Aquanty, we've focused up until recently on science and R&D, so we're very much new to the whole concept of market development. We're getting better at it, but this is where I think we're looking for collaborators.
Yeah, thank you so much, Stephen. This was an intriguing talk, and I'm sure there's lots more questions that people didn't get to ask, so we will forward those to you later. Thank you so much.
Yeah, I'm happy to answer questions.